Welcome to the first lecture of the application module. I'm Michele Laureni, an assistant professor in bioprocess engineering at TU Delft. In this lecture, we will explore a process called Sharon, which exemplifies the use of microbial selection principles for engineering design and efficient nitrogen removal from wastewater. To this end, we will start by briefly exploring how nitrogen is typically removed and reflect on the stoichiometry of the processes involved. Next, we will identify possible selection mechanisms and discuss their practical implications. Conventionally, ammonium is first oxidized to nitrite and subsequently to nitrate by ammonia and nitrite oxidizing bacteria, AUB and NOB respectively. This requires exogenous oxygen as electron acceptor, which represents a substantial operational cost. The produced nitrate is then reduced to N2 via denitrification, a process requiring an electron donor, typically organic carbon, expressed in terms of chemical oxygen demand, or COD. While in most designs the organic matter already present in wastewater is partially used for this, external organic carbon addition, example methanol, is common and represents an additional cost. By recalling the stoichiometries of the individual catabolic reactions, we can now estimate the oxygen and COD required per ammonium removed. Here, acetate is used as the organic carbon source. Subsequently, by including the respective anabolic reactions, we can estimate the total consumption as well as the resulting biomass production in terms of kilograms volatile suspended solids, or VSS, per ammonium removed. In principle, if the process is stopped at nitrite, then both oxygen and COD requirements for complete nitrogen removal to the nitrogen gas can be reduced, along with the biomass produced. As we did before, we can write down the stoichiometries and estimate the oxygen and COD consumption and biomass production per ammonium removed. This results in a net 25 and 40% reduction in oxygen and COD and roughly 30% less biomass. From an engineering perspective, the central challenge is to identify the selective pressure to promote the growth of AUB and prevent the one of NOB. AUB and NOB compete for the same electron acceptor, oxygen, and NOB relies on AUB for nitrite. Moreover, NOB also features a higher sensitivity to free ammonia and free nitrous acid, and salinity. But even more importantly, the respective maximum biomass-specific growth rates, μmax, vary as a function of pH and temperature, with AUB growing faster than NOB at higher temperatures. In this graph, the inverse of their μmax, corresponding to the minimum/retention time required to stay in the system, is plotted as a function of temperature at a pH of 7. As can be seen, above 20 degrees Celsius, AUB require a lower SRT. In other words, grow faster than NOB. By maintaining the aerobic SRT, for example, at 1 day, above 28 degrees, the growth of AUB can be promoted while NOB are washed out. The SRT can thus be used as the sole selecting factor to favor AUB over NOB. On this simple principle, the Sharon process, an acronym that stands for Single Reactor System for High Activity Ammonia Removal over Nitrite, was developed at TU Delft in the 90s. In 1999, the first full-scale Sharon reactor was implemented in Rotterdam, only 3 years after the first idea was developed. The process was implemented to treat the reject water from anaerobic digestate dewatering facility in the Dockhaven wastewater treatment plant, with high nitrogen and low COD concentrations, and accounting for about 15% of the total nitrogen load. In this initial design, the effluent of the Sharon process was recirculated to the inlet of the conventional wastewater treatment plant to be denitrified with the influent COD. Specifically, the process is operated as a simple, continuously mixed reactor with without biomass retention. In other words, the total hydraulic and solids retention times coincide. The aerobic retention time is maintained around 1 day. This simple operation allows to retrofit existing infrastructures, a thickener here in Rotterdam. The temperature is maintained between 30 and 40 degrees Celsius, thanks to the influent temperature coming from anaerobic digestion and the significant biochemical heat production due to the high inlet concentrations. In fact, the reactor often requires cooling. An important consideration is that operation at high temperature is not possible directly on municipal wastewaters. The control of the pH is also essential, owing to the acidifying of the ammonia oxidation process, consuming 2 moles of alkalinity per mole of ammonium removed. The influent alkalinity typically compensates for about 1 mole of alkalinity. The remaining is provided via denitrification, typically with methanol addition. Denitrifying conditions are achieved by alternating oxic-anoxic conditions. In terms of process configuration, the Sharon process can be implemented as a single or 2-stage process, where the nitritation and denitritation reactors are in series. Denitrification can be implemented only for pH control or for full nitrogen removal. Ultimately, a very interesting Sharon implementation is a combination with Anamox for fully autotrophic nitrogen removal, as we will learn in the Anamox application lecture. To conclude, in the single-stage configuration of Sharon reactor, at least half of the influent nitrogen is removed in the form of dinitrogen gas, as denitrification is used to control the pH. Effluent nitrate is negligible, and the residual ammonium and nitrite are recirculated back to the main wastewater treatment plant for further treatment. Importantly, thanks to the nitrite shortcut, the Sharon process allows significant reductions in oxygen and COD requirements for the removal of ammonia. This is achieved by a simple operation using the aerobic solids retention time to promote the growth of AOB and wash out NOBs. The most successful implementation is on high strength and high temperature effluents, devoid of easily biodegradable COD.